Right, so our next theorem that we're going to present is a way that you can show a function is not uniformly continuous on a set. But in practice, it's a little bit more specialized than that. So the sort of easiest way to show a function is not uniformly continuous on a set is if you can find the point at which it's not continuous. Right? So if it's not continuous at a point in the set, it has no hope of being uniformly continuous on the set. So this theorem is actually more useful in the more subtle case where the function is continuous on A, but it still fails to be uniformly continuous on A. So we can actually say a little bit more based on the previous theorem. It's most useful in places where you have a continuous function and a non-compact set. Then this theorem is useful for establishing non-uniform continuity, right? Because if it was a continuous function on a compact set, you'd be done. It would have to be uniformly continuous. And if it's a function that's not continuous at some point, then it can't be uniformly continuous. So we have this sort of specialized situation where you've got a continuous function, you're not sure if it's uniformly continuous, you have a set that isn't compact, then this theorem can be used to demonstrate lack of uniform continuity. Now, showing that something isn't the case can be a little tricky because you have to have a firm grasp on the negation of the definition. And our definition for uniform continuity is kind of involved. So first, okay, so let's state the theorem. F is not uniformly continuous on A if and only if there's some epsilon and two sequences in A so that the difference in the sequences converges to 0, but still the difference in the function values are always bigger than or equal to this epsilon. So we get sequences that are sort of converging to each other, but the function values can't be made close to each other. So that is going to be enough to show that the function is not uniformly continuous in the set. Okay, but we need to prove this. It's an if and only if statement, so we have two directions to prove. The first one is, let's suppose that F is not uniformly continuous on A, then we have to construct a sequence like this that works. So that means that we have to have an idea of what it means for F to not be uniformly continuous on A. Well, the definition says it is uniformly continuous if for every epsilon bigger than 0, there is a delta bigger than 0 that works. And what I mean by works is that for every x and y that are within delta of each other, f of x minus f of y is less than epsilon. So we have to, if that's not the case, what that means if for every epsilon isn't true, that means there is an epsilon for which the rest of it doesn't work. So we have there exists an epsilon bigger than 0, because not every epsilon will work. So there's got to be one that doesn't. So there exists an epsilon. And if it doesn't work, that means for every delta, we can find points in A that are delta close to each other. So x and y in A such that x minus y is less than delta, but that doesn't imply f of x minus f of y is less than epsilon. Right, so this is, I mean, it's a lot to do, and it's a little subtle, but this is negating the definition of uniformly continuous. So if uniformly continuous means for every epsilon there's a delta such that if x and y are close enough together, then f of x minus f of y are less than epsilon apart. To say that isn't the case means there must be some epsilon for which no matter what delta we pick, right, so there doesn't exist a delta. So for every delta we pick, we can find x and y in A that satisfy the closeness requirement of x and y, but don't satisfy f of x minus f of y less than epsilon. Right, so that takes some thought to get used to. Right, so there's some epsilon for which the definition of uniformly continuous fails. What does it mean for an epsilon to fail? That means we can't find a delta that makes the rest of it work. In other words, for every delta, no matter what delta we try, we can always find points in A within delta of each other, but whose function values do not get close enough together. Now, understanding this definition is most of the work in the proof. Right? So with this definition for not being uniformly continuous, then what that means is there exists xn and yn such that for the particular choice of delta 1 over n, we get f of xn minus f of yn bigger than epsilon, and so we've created the sequence. Xn and yn are the two sequences. Right? And now we have to prove the other direction, but again, the hardest part has been done. So let's assume that we have two sequences for which this is true. So let xn, yn such that they go to 0. But even though xn and yn get as close as we like together, their function values do not. Well, if that's the case, then we've basically we've shown what we need to show, because no matter what delta is, so for any delta, let's take n large enough that xn minus yn is less than delta, and that basically completes the proof, right? Xn and yn are both points in A. Because xn minus yn goes to 0, I can make this less than any pre-assigned delta, but by construction, the f of xn minus f of yn we know to be bigger than or equal to epsilon. And that completes the proof of the theorem. Right, so the hard part really is understanding the connection between the definition of uniform continuity and the definition of what it means to not be uniformly continuous. And then with that understanding, we can translate it into a fact about particular sequences in A, so that the sequences get arbitrarily close together, but the function values don't get within epsilon of each other. Right? And in the next video, we'll do a quick example of that.